Hello, my name is Hyunju Lee, an undergraduate student at Gwangwon University, and this is our presentation for the 2025 KICS conference. And today I will introduce our study on the development of a self-power pressure sensor and smart installer for gait and activity analysis. And here is the contents of today's presentation. Real-time gait monitoring is essential for the diagnosis and rehabilitation of neuromuscular disorders. However, conventional gait analysis systems are limited by battery dependence, restricted operation time, and spatial constraints. To overcome these issues, the study developed a self-power gait analysis sensor based on a triboelectric nanogenerator. The developed TNG sensor was integrated into shoe insole to evaluate applicability in the real-world environment. The insole system successfully detected not only common activities such as walking and running, but also subtle micro-movements observed in patients with Parkinson's disease. And for real-time wireless data transmission, a dual Arduino-based Bluetooth communication architecture was established. Also, the processing application was utilized to transmit digitized sensor signals through the serial port and visualize the data in real time. This allowed effective analysis of applied pressure on sensors, gait patterns, and the temporal variation of sensor signals. The tribopositive layer COPU and the tribonegative layer PVDF of the sensor were fabricated as follows. The electrospinning was utilized as a crucial step during fabrication. Electrospinning is a representative technique for fabricating nanofibers by applying a high voltage to a polymer solution or melt, producing continuous fibers with diameters ranging from several tens of nanometers to a few micrometers. The most distinctive feature of electrospinning is its ability to create nanofiber mass with a large specific surface area and high porosity, which are advantages for enhancing charge storage and transfer efficiency in triboelectric nanogenerators. The internal structure follows a 7-layer stack. PI film acts as protective insulators, fabric electrode collect charges, PVDM nanofibers store negative charges, COPU nanofiber generate positive charges while enhancing durability, and the spacer regulates the air gap. When two materials with different electrical affinities come into contact and then separate, charges are transferred and the potential difference is created. By repeating this process, the sensor continuously generates electricity, providing a reliable energy source without the need for frequent charging or replacement. And it operates in a completely self-powered manner. COPU composite exhibited enhanced dielectric properties, increased surface roughness, and improved mechanical elasticity. The high surface density and electron donating ability of the porous cup structure significantly increased the charge density. PVDF is a well-established dielectric material that tends to accumulate negative charges upon contact, making it widely adopted in triboelectric applications. When electrospinning into nanofibers, PVDF exhibits enhanced diapole alignment in the beta phase, which significantly improves its ability to generate and retain surface charges during mechanical interactions. Fabric electrodes are textile-based conductive substrates that maintain the intrinsic mechanical flexibility of fabrics, making them highly suitable for wearable electronic devices and energy harvesting systems. PI film provides excellent electrical insulation, preventing short circuit between electrodes and ensuring stable electrical operation. Also, it offers high mechanical strength and flexibility, protecting the electrodes and triboelectric layers from external mechanical stresses such as repeated pressure, bending, and friction. The TNG sensor generates alternating output voltage in the range of 20 to 30 volts under mechanical stimulation. However, this level exceeds the allowable DC input range of Arduino Nano. Therefore, a signal conditioning circuit is required to rectify and attenuate the high voltage output for safe data acquisition. For rectification, a bridge diode is used to convert the AC output into a unipolar pulsating DC waveform. At the rectifier output, an RC parallel network is connected to stabilize the signal. The resistor network attenuates the voltage and limits current flow, while the capacitor smooths the waveform and suppresses the noise. Then the gate signals are digitized by the Arduino Nano and transmitted wirelessly via an AC05 master module. An AC06 slave module receives the data and forwards it to the Arduino Nano, where the signals are ultimately used for gate pattern analysis. The two figures show the voltage obtained in the contact and separation mode. A positive charge is generated as electron movement occurs due to contact between the two travel layers. And when the two travel layers separate, the previously induced charges are rearranged, generating a negative voltage peak. Through the experiment in the first figure, it was clearly found that the thickness of the PVDM nanofiber increases as the volume of the solution increases. And through the second figure, the highest voltage was observed when the PVDM thickness was about 16 micrometer, so we decided it as the proper thickness. Lastly, the third figure confirms that the TNG sensor responds sensitively even in the low pressure range, generating a sufficient voltage difference for reliable detection. The first figure shows that PU produced an output voltage of approximately 50 volt, whereas CPU generated about 100 volt, indicating superior performance. This is attributed to the presence of highly electronegative atoms, which facilitate more effective charge storage. The second figure presents the surface potential of each material. PVDF exhibits a surface potential of approximately -100 volt, whereas PU and CPU show about 40 volt and 80 volt respectively. A larger surface potential in the triboelectric layer is generally associated with higher interfacial charge density and more efficient charge transfer, thereby contributing to an increased output voltage in TNG devices. The figure in the left shows the raw voltage from the TNG sensor, measured before the ADC circuit, to provide a clear comparison. We confirmed that a maximum voltage peak is generated at the moment of a hail strike. The signal amplitude at this point is larger than that from other movement or noise, making it the clearest and the most stable criterion for distinguishing individual steps. In the right figure, SNR is an index that indicates how much stronger the valid signal is compared to the noise, and is commonly used as a measure of a signal quality. In this study, our data sets consistently showed SNR values in the 26 to 32 decibel range, which indicates that the signal was clearly distinguishable from the noise. These figures show analysis in the gate in 10-second interval, defining an event as the point where the voltage exceeds 3 volt at the hail strike. While walking, the dominant pattern consisted of repetition intervals in 2-second range, and the average frequency was approximately 1.5 Hz. And while running, a distinct rapid repetition was around 1.6 seconds, and frequency was approximately 1.7 Hz. And an event occurs around 4.5 seconds, corresponding to a frequency of 1.2 Hz for the subject with a disorder. This video presents the real-time monitoring interface while the subject is walking. And this video presents the real-time monitoring interface while the subject is running. In summary, we successfully fabricated a high-power TNG sensor by assembling CPU nanofibers as a tribo-positive layer and PVDM nanofibers as a tribo-negative layer. And also MCU processed data were transmitted wirelessly via a Bluetooth module to a separate receiver display device for real-time monitoring. In this study, we further anticipate that gait can be monitored in real time through wearable devices, enabling users to correct their walking patterns. In addition, collected data can be transmitted to healthcare professionals for remote monitoring and to support continuous care. And here are the references we used. This concludes my presentation. Thank you.